Hello, I'm Hugh Manfield and welcome to my science channel. Now today I'm going to be talking about something that I covered in my book Einstein and Aliens in Appendix 6. And I briefly covered it in another video on black holes, but this subject really deserves a video of its own. And it explains why our entire concept, the classical concept of matter, is entirely wrong. So the classical concept of matter was developed by the ancient Greeks and the Renaissance philosophers, and in the late 1800s when Einstein was growing up, it was the world view at the time. And that view is that there are little bits of stuff that we call matter, and this stuff moves around in a void of space. And that's pretty much the philosophy up to this day. There's matter and there's space. There's objects and there's the space in between them. And that seems to be the way the world works. But if you follow fluid space theory, you come up with an entirely different point of view. So Einstein stuck to his classical point of view, and when he developed the black hole, he needed some place for the matter to go. In the case of the traditional black hole, all the matter gets pulled down below the event horizon and compressed into a singularity. And everyone loves the singularity and they think it's really cool, but it's wrong. In fluid space theory, space-time itself flows inward in sync flow in a gravitational field. And I've illustrated it here with unit cubes of space-time, and they're all falling inward at escape velocity. That's the velocity vector field of gravity. And as they get faster and faster, as they move to the center, they become length contracted. So there's a loss of volume. This is the basic idea behind fluid space theory. Now, gravitational fields are spherical, but we can study them by extracting a cone. Out of that field, you can get a cone-shaped object. You can study fluid flowing down that cone as if it's flowing down a funnel and becoming length contracted. And as it does that, the actual internal shape of the funnel changes from a straight traditional cone to a hyperbolic funnel, where the sides, the taper angle of the sides becomes less and less until at the event horizon it becomes a straight pipe. The fluid flowing down a cone will become faster and faster as the area decreases. But in a straight pipe, the area is no longer decreasing and there's no acceleration. So fluid space theory tells us that at the event horizon, gravity goes away. There's no acceleration. Now this is the part from Appendix 6 where I calculated the energy in a gravitational field. And to do that, I took a volume of space. In this case, we have a cylinder, and that cylinder is moving at some velocity, and that velocity is increasing as it falls in toward the center of a black hole, and it becomes length contracted. And I express that length contraction as a strain. This is an engineering term. It's the uncontracted length minus the contracted length divided by the uncontracted length. And what this gives you is a number between 0 and 1 that defines the amount of contraction, the amount of compression that's in an elastic material. And this is a typical stress-strain diagram. And you have the strain from 0 to 1 and the stress. The slope of the curve is Young's modulus. So the stress is equal to Young's modulus times the strain. And if we want to compute the area under the curve, which will be the amount of energy stored in the elastic material at any given strain, we can say the energy is equal to 1/2, because we're taking half the rectangle, and the rectangle is the stress times the strain. So we have Young's modulus times the strain, and we have the strain itself, so we get Young's modulus times the strain squared. And that's how in engineering we compute the stress or the energy in a volume of material. Now the volume of material is important because the energy is per volume. So if you want to know the actual amount of energy within a given volume of material, you multiply that times the volume. And that's why we have volume here in the equation. So if we find out the amount of energy, it's half the volume times the Young's modulus times the square of the strain. So pretty simple, basic engineering. So how do we apply this to a gravitational field? Well, first of all, like I said before, gravitational fields are spherical, so we need to use a cone rather than a cylinder. And it's well-known geometrical fact that the volume of a cone is 1/3 the volume of the cylinder. So we're going to come up with a shape factor to transfer the cylinder into a cone. And that shape factor is 3. We want all of the energy in the cone that we had in the cylinder. And we just increase the Young's modulus by 3, and we have our shape factor to transfer the cylinder into a cone. Now we also want the strain expressed as a radius. And we can do that because we know the velocity as a function of radius is escape velocity. We plug that into our strain equation and we come up with an equation for strain as a function of radius. And that's based on a gravitational body with mass m. So if we just have a cone, that's going to give us a partial energy for the field. But we want the total energy for a spherical field. Well, luckily, you can pack cones basically into a sphere. And if you pack in enough of them, then all you have to do is sum up the volumes of all the cones and you get the volume of a sphere. And if you want the area of the sphere, you sum up all the areas of the bases of the cones and you get the area of the sphere. So in our equations, we will plug in the volume of the sphere and the area of a sphere. And there's one more thing that we need. We need to know what is the Young's modulus of space-time. And it turns out that c to the 4th over g has units of newtons. And Young's modulus is in terms of newtons per square area, or per length squared. So let's try c to the 4th over ga. And in this case, a will be the area of the sphere. And then we apply the shape factor, and we have the Young's modulus equals 3c to the 4th over ga. So now we're ready to calculate the energy within a gravitational field. So here's our equation for energy from going from a strain of 0 to 1, and whatever strain level we have, we just plug that in. So we have 1/2 volume of the sphere times our Young's modulus with the area of the sphere plugged in, and our equation for the strain as a function of radius. So a lot of these terms cancel out, 4's, pi's, 2 of the r's, the 3's, and we end up with a much more simple expression, c to the 4th r over 2g times the square of the strain. And that will give us the amount of energy in a gravitational field from infinity into a particular radius. And whatever radius we choose based on the strain, so we could calculate the field energy of the Earth from infinity down to the surface of the Earth. But we're working with a black hole. So let's plug in the Schwarzschild radius, the radius of the event horizon, and calculate the amount of energy that's in a gravitational field from infinity down to the event horizon. And it turns out when we plug in the Schwarzschild radius, everything cancels out and we get the energy of a gravitational field equals the mass times the speed of light squared. And this is a famous equation. This is Einstein's matter energy equivalence equation. But I've come about it using a totally different method. I've used the method of gravitational energy. So what does this mean? What does this tell us? Well, it tells us that the energy in a gravity field equals the rest mass of the body. But wait a minute. If there's matter and the energy of the gravitational field is added to that, then that would make the mass more than the rest mass. Well, there is not matter. The matter is the gravitational field. The energy is the gravitational field. The particle and the gravitational field are one and the same. So what else does it mean? Well, since there's no such thing as matter in the classical concept, then matter does not curve space-time. Matter is curved space-time. So matter as Einstein conceived it does not exist. The classical concept of little bits of matter moving around in a void of space is completely wrong. There's no little bit of material with the properties of mass, momentum, and gravitation. The gravity field is the mass. The gravity field is the momentum. The gravity field has all the energy. And this is a basically different concept of the existence of matter from the classical point of view. So if we look at Einstein's, or the traditional black hole, gravity vanishes at the event horizon. All of the energy of the field is from the event horizon outward. So there's really nothing left to fall below the event horizon and nothing left to be compressed into a singularity. Fluid space theory says that at the event horizon, the tapering of space-time, the curvature of space-time becomes tangent, and from the event horizon below, there's just an endless corridor of zero-g space-time. There's no more gravity. Gravity comes to an end at the event horizon. And there's nothing left to fall. There's nothing left to accelerate. There's no more acceleration. There's no more force at the event horizon to pull anything in. So let's look at Einstein's famous quote, and everyone brings this out when they want to pretend to be smart. Matter tells space how to curve, and space tells matter how to move. Now, this sounds totally reasonable, but let me read it back to you now. Knowing that curved space is matter, I'll substitute matter with curved space, and now it reads, curved space tells space how to curve, and space tells curved space how to move. You see, it's total nonsense. It's gibberish. And the thing is, it always has been. Einstein's basic philosophy in developing general relativity was wrong. He separated matter and energy from space. Well, there is no separation of matter and energy from space. Matter and curved space are one and the same thing. So the foundation of Einstein's field equation is completely wrong. So what does fluid space theory have that general relativity doesn't? Well, it has a dynamic component, and I call this ruach. It has the flow energy, the divine wind or motion in the background of space-time. And with this inflow, matter is created by the storage of energy in the curvature of space-time. Without the inflow, the energy wouldn't be stored. And without the inflow, the energy wouldn't be stable. If you just took a bunch of energy and compressed it into a small place, it would just disperse into the cosmos, and it may create photons and particles. This is basically what happens at the Large Hadron Collider. They bring a bunch of energy. During the collision, the energy is released into a very small space, and it dissipates out, and it condenses out particles, and they scatter. So that's basically what would happen if you put a bunch of energy into a small space without the ruach field, without the inflow field. But the inflow field, the gravitational field, binds that energy and holds it together. And that's why black holes don't poof away. That's why all the basic particles of matter don't just decay away into nothingness. That's how matter gets its stability. Another thing, if you have energy condensed into a small space, but you don't have the inflow field, you won't have gravity. The inflow field, the acceleration of space-time as it moves down the funnel, is what creates gravity. So another thing wrong with general relativity is the concept that energy itself will create gravity. Well, it won't. If you have a concentration of energy without the flow field, it won't create gravity. And this is something that's completely missing from general relativity. So looking at the fluid space theory philosophy of space and time, what we see are tiny voids, bubbles, discontinuities in space-time that move around and are connected by fields. This is completely opposite of the classical view of matter and space. We see that the substance of the universe is the space and the field, and what we call particles are actually the voids. So it's completely the opposite of the classical point of view, completely the opposite of the way most people think about space, time, and matter. And what this means is that the universe is one single thing, one single infinitely complex object. It is basically the everything, and we're all part of it. So what else can we draw from this derivation of the energy within a gravitational field? While all matter is energy, not all energy takes the form of matter. You can have a vast amount of vacuum energy and it will just sit quietly in the background doing nothing, and it won't even curve space as general relativity says that it should, because it doesn't have a flow field. It's just sitting quietly. It's more like a hydrostatic situation. So the energy without the Ruach field will not create gravity. And Einstein's ideas on cosmology are therefore all wrong. Now, general relativity is deep in the foundation of the lambda cold dark matter model, and that's going to be really hard to change. And what it means is that current physics is bound to a false belief system. And you think, yeah, that's probably true. There's signs of it. 95% of the cosmos is some unknown material, dark energy, dark matter. Well, that's pretty much a fail. If you only know what 5% of the cosmos is, you've basically failed in describing it. If you got 5% on a test, that's like even below an F. That's like embarrassing, okay? So the current best they can do, lambda cold dark matter, is actually pretty pathetic. Let me try and explain this with the bootlace analogy. And I'll go through the current state of cosmology as it's been bootstrapped. And sorry for the fine print here, but there's a lot of stuff to fit in. So we started off with Newtonian gravity, and everything seemed to be fine until electromagnetic theory came along and was in conflict with that. Galilean transforms didn't work with electromagnetic theory. But Einstein fixed that with special relativity, and he secured himself a place in history for that. That's probably his best work ever. But he was young and he wanted to do more, and he came up with general relativity. Well, people started looking at the math and they said, hey, Dr. Einstein, your math implies that the universe should be expanding. There's actually a solution for a contracting universe, but apparently they figured that if it was contracting, it would have disappeared. So they threw that contracting solution out. So Einstein said, oh, well, that's clearly wrong because we live in a static universe. We live in a steady state universe which consists of the Milky Way galaxy. And that's all there is. So he added the term lambda to create a steady state universe. But then Hubble began to discover that there were galaxies outside the Milky Way. And those galaxies had a cosmological redshift, which is explained in one theory by an expanding universe. So Einstein said, wait, no, I was wrong. That was my biggest blunder. I'll take lambda out. And we're back to relativity again. So we developed the Big Bang theory with Hubble expansion. But then that still wasn't quite right because we couldn't explain why the universe is so even and flat in all directions. So we added cosmic inflation. And for each one of these discoveries and changes, we've added more and more laces to the boot, and the boot has grown taller and taller and taller. And then we discovered that the rotation curves of galaxies didn't match Newtonian gravity. So we added dark matter, or MON, and we added more laces to the boot. And then we discovered the expansion of the cosmos seems to be accelerating. So we added more laces to the boot, and we brought back lambda, and it gave us dark energy. So now we have this very tall, unwieldy boot for the lambda cold dark matter model, and it's uncomfortable. No one really likes it, but if you fiddle around with the laces enough, you can get it pretty much to fit the data. But the real problem with the boot is down here at general relativity. And to fix that, what physics would have to do is unlace the boot all the way down to general relativity, come up with something different to replace it, and then start lacing it back up again. And that's a lot of work. And there's no one in physics that want to do that. They're not happy with the model the way it is. They think there ought to be something better. But there's no one with the authority or the clout or leadership in physics that can say, let's do it. Let's throw it all out and start from scratch again, which is what they really need to do. But there are physics departments and papers and citations and Nobel Prizes. They'd have to admit that 80 or 90 years worth of what they've been saying is completely wrong, and they just can't do that. It's too much work. But if they did, you would adapt the fluid space theory declining vacuum energy model. And it starts out the same with Newtonian gravity, electromagnetic theory, special relativity. We get a few laces, and then fluid space theory and declining vacuum energy to explain the cosmological redshift. Fluid space theory includes dark matter, the effects of what we call dark matter, and the effects of what we would call dark energy. So really, with fluid space theory and declining vacuum energy, all you need is a regular sized boot. And the reason this works is that general relativity is no longer causing any problems down at the bottom of the laces. That's still going to be too hard to change. So we're basically stuck in a world where we have to keep Einstein's general relativity and keep teaching it and keep trying to use it, even though it's really wrong. And there's an easier way that can make things much simpler. Will it ever happen? Who knows? But as they say, if the boot fits, wear it. So until next time, I'm Hugh Manfield.